In this video, I'm going to discuss pH and buffers. And by the end of this video, here's what I'd like you to be able to do. I'd like you to be able to define pH in regards to the dissociation of water. What are they in relationship to each other? I would like you to define the relationship of pH and hydrogen ion concentration. I would like you to describe how acids and bases affect the pH of a solution. I'd like you to be able to describe the characteristics of a buffer, explain why buffers must be weak acids, and cite examples of why pH is important in biology. So, pH. In order to understand pH, we need to understand the idea that any aqueous solution, that is, any solution that contains water, some of those water molecules are going to dissociate into ions. So let's take a look at that. What we have here are two water molecules, and we have a hydrogen bond between them. Very rarely what happens is this hydrogen bond sort of goes too far, where this oxygen actually steals this hydrogen, the proton of this hydrogen, okay? Right, so it's not stealing the electron of this hydrogen, it's stealing the proton and the neutron of this hydrogen, which means that we're going to have something called OH3 or H3O. So it'll have one extra proton than electrons in this molecule. And so what we'll have is a full positive charge. Now, this water molecule here, the one that lost the hydrogen's proton and the hydrogen's neutron, still has the hydrogen's electron, which means the resulting ion here is formed and it has an extra electron, and so one negative charge. So the dissociation of water leads to the production of a hydronium ion and a hydroxide ion. Now, most of the time, we don't really talk about hydronium ions like this. We sort of look at it like this, a hydrogen ion. So sometimes I will call this a hydrogen ion. Sometimes, and probably most of the time, I will call this a proton, because that's pretty much what this represents, is just the proton and the neutron of the hydrogen atom. And this here is, of course, an O and an H, and then an extra electron from this hydrogen atom here. Okay, so this is what we're going to be concentrating when talking about pH, the hydrogen ion concentration. So we might have a solution that has lots of hydrogen ions. So this has a hydrogen ion concentration of 1 × 10⁻³ . This one here doesn't have nearly as many. It's got 1 × 10⁻⁹ molar hydrogen ions or protons. Here's the problem. Saying 1 × 10⁻³ molar hydrogen ion concentration takes a million years to say. Oh, that's 1 × 10⁻⁹ molar hydrogen ion concentration. It's just a pain in the butt to talk about because it's a long-winded term. So what scientists have done is simply develop the term pH. And the pH is just another way of expressing the hydrogen ion concentration of a solution. The pH is the negative log of the hydrogen ion concentration. So in pure water, the hydrogen ion concentration is 10⁻⁷ molar. The pH is minus log of that, so that means the negative log of 10⁻⁷ is 7. So it's much easier to say, oh, this solution here is pH 3, is way easier to say than saying, oh, the hydrogen ion concentration of this solution is 1 × 10⁻³ molar. They mean 100% the exact same thing. pH 3 is just another way of saying this. pH 9 is just another way of saying this, okay? But one thing you've got to be careful about, because of the idea of this negative log, right? 1 × 10⁻³ molar is greater than 1 × 10⁻⁹ molar. This is a greater hydrogen ion concentration than this. But when you take the negative log of that, that gives us a pH of 3 versus a pH of 9. So the lower the pH, the higher the hydrogen ion concentration. The higher the pH, the lower the hydrogen ion concentration. pHs range from 0 to 14. Anything less than 7, any solution less than 7 is considered an acidic solution. Anything greater than pH 7 is considered a basic solution, and then anything right at pH 7 is considered to be neutral. Acids are going to be molecules that when you add them to a solution, they will increase the hydrogen ion concentration, or in other words, lower the pH. Bases are going to be chemicals that when you add them to an aqueous solution, they are going to lower the hydrogen ion concentration, or in other words, they're going to raise the pH. Now, why is it so important to know the hydrogen ion concentration of a solution, to know the pH of a solution? Well, it turns out that the concentration of hydrogen ions in a solution has all sorts of ramifications. We are going to talk about protein structure and how the pH affects protein structure a little bit later, but let's take a look at this example here. We're looking at the oceans, and there's all sorts of marine life out there that require a molecule called calcium carbonate for their shells. And the way you make calcium carbonate is you take this carbonate molecule, you take some calcium, and you get calcium carbonate. The problem is that this carbonate not only reacts with calcium, which is good, it also reacts with a hydrogen ion to make bicarbonate, which means the more hydrogen ions in solution, the more of this carbonate atom is going to be sucked away to make bicarbonate, and there's going to be less of it around to make calcium carbonate. All right, well, how are we getting more and more hydrogen ion concentration in the ocean? The levels of CO2 in the atmosphere is increasing. That dissolves into the water to make carbonic acid, which then releases its proton, increasing the concentration of protons in the ocean. So the oceans are becoming acidified. They are getting more and more and more protons. All those extra protons are sucking up all the carbonate, making bicarbonate here, and we're having less and less carbonate to interact with calcium to make calcium carbonate, and now our marine life is suffering for it. They're not able to make their shells quickly enough and sufficiently enough and are starting to die. So this is an example of why it's so important to understand the amount of hydrogen ions in a particular solution. And brings up the next point. It's really important to regulate this, to have a way of sort of maintaining within a very strict window the amount of the concentration of protons in a solution, or regulating the pH. And that's the job of a buffer. A buffer is a solution that minimizes change in pH. So let's take a look at the characteristics of buffers. As I said, they minimize changes in pH. They don't stop the changes. All right? That's important to understand, and we'll look at some data in another slide here in a second. And each buffer, there's lots of different types of buffers out there. Each buffer has a specific buffering range. Some of them buffer best at low pH, maybe pH 2 or 3. Some of them buffer best at higher pH, so maybe pH is 10 or 11. Some buffer best at intermediate pHs. So based on this, what's really important to understand is that buffers don't necessarily keep the pH at 7. I think that's a misunderstanding that many of you might have had. Some buffers work best at lower pHs, some at higher pHs. It simply depends upon the buffer that we are using. Now, blood, for example, has a pH of about 7.4, and it needs to be right around that pH. And so blood has buffers in it to minimize any change that might occur to the pH of that blood. Let's take a look at some data and see exactly how buffers compared to non-buffered solutions. In black and red, we have water. This is an image from fish tanks, if people are trying to buffer their fish tanks. And so I pulled this off the web. So we have basically two versions of water. Here I have tank water that obviously has some other stuff in it, and then we have pure water. And here on the y-axis is pH, and here on the x-axis we are adding more and more and more acid. Okay? And in blue we have a buffered solution, tank water that's had sodium acetate added to it. So look at what happens. When we add just a little bit of acid, so let's say 5 units of acid here, we go from a pH way up here, boom, right here, and right here. So we go from a pH 7 or 8 to a pH 3 or 4 with just a teeny bit of acid added. But look at this. The same amount of acid that we add that made these guys go down, what, 5 pH units? Look at this. The buffered solution only went down maybe 1 pH unit. So that's a buffer. It minimized the change in pH. Notice it still went down in pH. It still went from about 8 to about 6 or something like that. But it, compared to a non-buffer, that change is quite minimal. Okay? So that's really important to understand, that buffers minimize changes in pH. They don't stop changes in pH. If you add enough acid to this buffered solution, you'll still get it to go down to those really low pHs here, but you've got to add quite a bit of acid to do so. All right, let's take a look at the molecular reason that buffers work the way they do. And the important thing to understand is that buffers are weak acids. And what that means is if you put, here's our weak acid, carbonic acid. When you put it into a solution, so when you put this molecule into solution, it does not dissociate 100%. Some of the molecules will dissociate, so you will get some protons in solution. You will get some bicarbonate ions in solution, but it doesn't break down 100%. You still have molecules that haven't broken down, so some of those molecules stay intact, stay intact, stay intact. So what we see here is when you put a weak acid into an aqueous solution, some of the molecules stay intact, and some of the molecules dissociate. And this is really, really important, because what this means is in this solution, we have molecules that look like this. This is called the conjugate base. It has the ability to suck up some protons to become that, the acid. In this solution, we have some molecules that have not yet dissociated that can, if we start running low on protons, they can break down to supply some more. So the fact that we have both dissociated and non-dissociated molecules in here means we can both donate protons when some have been taken away, or accept protons when too much has been added to the solution. So let's take a look at that. Here, right, so we're at an equilibrium. Okay, we added our carbonic acid and we reached an equilibrium between the conjugate acid and the conjugate base. Okay, so we're at equilibrium. Now, let's say that now we add a strong acid to that buffered solution. Right? Adding a strong acid means we are increasing the hydrogen ion concentration. Well, that's going to mess up our equilibrium. Right? So now if we've suddenly increased the hydrogen ion concentration, we are going to drive this reaction in the reverse direction. These bicarbonate atoms, are going to suck up some of these extra protons, and become the conjugate acid. Okay, and in doing so, we're sort of minimizing that change in pH. The opposite is also true if we were to add a base to this solution. So a base, remember, a base reduces the hydrogen ion concentration. Okay, so we've reduced the concentration of one of the products. So this is just a chemistry thing, right? When you reduce the concentration of one of the products, you're going to shift the equilibrium, right, in the forward direction. More of these guys are going to break down to supply some more protons to make up for the ones that we've taken away with the strong base. Okay? And that is exactly how buffers work. They have the ability to react in either way. They can react to an excess of protons by sucking them up, so going in the left-hand direction, or they can react to a reduction of protons by supplying more. The reaction will move to the right. All right, so here is a nice problem, and I want you to pause it here, and I want you to try to solve it. So I'm going to give you a second to pause, and you can try to solve it. All right, I'm assuming you have tried to solve it. I'm assuming you have a piece of paper with some notes of you trying to solve it. So which is it? Is it going to react and shift to the left, or is this reaction going to shift to the right? So let's take a look at what we have. We have used carbonic acid to make a buffered solution. So what we did is we took water, and we added to it carbonic acid. Now, when we do that, that carbonic acid is going to reach an equilibrium. Some of it's going to break down, some of it's going to stay like this. Good. Now what we've done is we've taken another solution we call liquid X, and we're adding it to our buffered solution. And we know that liquid X is a substance of extremely high pH. And we've added it to our buffered solution. All right. So if we add a solution that is very high pH to our buffered solution, what are we doing to the hydrogen ion concentration? That's ultimately the key to unlocking the answer to this question. High pH means really low hydrogen ion concentration. So we're adding more liquid here to our buffer that has really low hydrogen ion concentration. What that means is what we're doing is we are reducing the concentration of protons in solution. This is going down. All right, if we are losing these protons, if the concentration of these protons going down, then this reaction has to shift in this direction. It has to shift from left to right. These conjugate acids have to break down to replace some of those missing protons. So the answer to this question is our reaction has to shift from left to right. So B is the answer.